me about HdpH. It's really Patrick Meyer's work, but Rob Stewart, Majal Saeed and myself are working on it. So what is it? It's a new distributed memory parallel Haskell. So for distributed memory architectures where there are a number of multi-core nodes connected together, it's implemented essentially in GHC. We really wanted to leave GHC unchanged. What's it for? Well, we're involved in a project where we're trying to do symbolic computation, think computer algebra problems in parallel on very large architectures. So we're designing for 1 million cores. The current architecture we're running on is about 90,000 cores. I'll show you some results on 2,000 cores. So you know how it's going. Essentially, the idea is to coordinate thousands of instances of the GAP computer algebra system. Computer algebra computations are highly irregular. They create tasks dynamically of wildly varying sizes. They differ in execution time by about 5 orders of magnitude in some of the problems we've worked on. So we need some dynamic workload distribution. On these big architectures, the time to communicate to a core close to you is very different from the time to communicate across the machine. So we need to think about controlling locality, and also we think there will be failures on these very large architectures. So what is it in one slide? Essentially, we take the scheduling mechanism out of the power monad, we combine that with the serialization mechanism from Cloud Haskell. Actually, we extend it somewhat to make it polymorphic, and it's actually truly polymorphic. There's no typical constraint. Edsco will say more about that in the context of Cloud Haskell later today. Function closures are now going to behave like functions. I'll explain that later. And we actually compute with closures. We create them, construct them, deconstruct them quite a lot. So in fact, we need a dual representation to make that efficient. So we keep the thump and the serialized version. The serialization is done lazily, so it's only actually done if you send the closure, so that we can cheaply construct and deconstruct the closures. The third element of the language is on-demand work distribution. So we use work stealing. In fact, we do 2 things. We have some explicit work distribution because we think you can't populate an architecture with 1 million cores lazily. You can't wait for all the 1 million cores to find the one core that has work at the beginning of the world. You have to explicitly distribute some work at the start, but then we'd like to use dynamic load management once the system's set up and the work stealing is out of the GUM runtime system. We also think that faults are going to occur in large architectures, so we have support for fault tolerance. Essentially, we have something called a supervised work pool, which guarantees that work closures are eventually evaluated under some reasonable assumptions. However, different to metapar, if you have fault tolerance, you lose determinism. So this is different to par and metapar. Sketch of the architecture, we've got nodes which are typically shared memory. They communicate via closures with other nodes. You can think of the nodes as essentially running a par-like scheduler. There are sparks and thread pools, if you're familiar with GUM, and there's a registry of references between distributed memory nodes. What are the constructs? Well, the first batch of constructs are just the constructs in the par monad. So pars, ivars, force evaluation, create threads, new, put, and get. In the distributed memory context, however, we have closures, rather like Cloud Haskell. We have global ivars, which is a serializable global reference to an ivar of type A. And when you put a closure into an ivar, it puts that value potentially on a remote machine. So that's a point where communication happens. And you can take a local IVAR and turn it into a global IVAR. You can take a closure, so push2 takes a closure and the name of a node and transmits that closure to that node to be executed. Spark is agnostic. It says it might be useful to evaluate this closure somewhere else, but it may or may not be evaluated. We do quite a lot of computing with polymorphic closures. So here's an application. AppC applies a closure of type A, or function type A to B, to a closure of type A and gives you a closure of type B. You can think of it as unclosure of the function. Can we steal a zapper? Oh, thanks. So unclosure the function, unclosure the argument, apply the two and create a closure of the result. Make closure preserves the original thumb together with the lazily serialized object. That's how it looks in theory. In practice, it's a bit more ugly because we don't have static in GHC yet. We do, however, have evaluation strategies, essentially functions that map now into par of A. This is along the lines of the strategy, the new flavor of strategies presented at Haskell 10. So you have a strategy as a function that maps from A to par of A. You can apply a strategy to a value of type A, and you create strategies. But strategies now contain lots of closure stuff. So I encourage you just to ignore closure when you read it, and you should read this as par list is a strategy. Given a strategy on A, or closure A, it gives you a strategy on a list of A. Or if you really want to read the closure stuff, if you're given a closure which represents a strategy on a closure of A, then you get a strategy on a list of closure of A, and then you can build things like ParMap, which does the obvious thing. It essentially preserves the computational part of the program, separates the computational part of the program from the coordination part. Okay, let's show you this actually working. So this is a very simple symbolic computation. It's not actually using gap for embarrassing reasons, but it's using only HdpH. We're essentially summing the result of mapping some function over quite a long list. It's running on an architecture called HIW, which is the largest architecture in the UK. This is quite a small instance of it. It's about 2,000 cores. And we have, as I said earlier, we've got this two-level coordination strategy. Explicitly send some work and then allow dynamic work steering to balance the machine thereafter. This looks at the speed up as you scale the number of cores for two data sets, and notice that we have slightly different numbers for the two data sets, slightly different numbers of explicit work distribution. So push explicitly distributes the work, and then you have a lot more local steering.
Is Totem a big calculation?
It's reasonably big well, it's actually really small on the number one.
Oh.
It's sort of find the highest common factor.
It's not just two floating point operations.
No,
That's all.
it's much bigger on 160k than it is on one, because it's slightly irregular. Fault tolerance, which I didn't tell you about before, we're starting to develop this. We've got this idea of a work pool where you essentially keep a record of all the closures you shipped off. If the node where the closure is running dies, you recover that closure and evaluate it elsewhere. And so the results I'm going to show you are from a slightly different function called Louville, which investigates a conjecture. So, runtime here, and then we introduce, we're running on 10 nodes, we introduce a failure at 10%, 20%, 30% through the execution of the program. If you run on 9 nodes, on 10 nodes, your execution time is just over 100 seconds. If you run on 9, it's just over 110 seconds. And you'll see that if you introduce the failure of one node, later and later in the computation, your runtime falls. So what else are we doing? We are doing more work on the fault tolerance. We're doing more sensible locality control. We're working on a profiler. The code is open source. There's a couple of papers, an IFL paper from last year and a TFP paper from this year, and that's it.